Day 2 Masterclass 2021. Today we will look at two of the major tools of Google Earth Engine. One is BFAST, the other is CODED. So these two tools are discussed in these two webinars, which you will see today. The first one is Faster Deforestation Monitoring with a BFAST, Breaks for Additive Season and Trend Monitor web application by Ms. Maevve and Ms.Laura. The second one is Remote Sensing Technologies in an Environmental Mapping Context by Ms. Crystal Westpeed, who has used coded tool of Google Earth Engine to study about the forests of Nepal.
Hello, everyone. My name is Maevve Naughton-Rockwell, and I am a college student currently based in the US. I am a rising senior and data science major at William & Mary in Williamsburg, Virginia. I'm here today to talk about a BFAST application I'm making with my partner, Laura Mills.
Hi, everyone. My name is Laura Mills, and I'm a rising senior also at William & Mary studying history and data science. I also serve as the Director of Data Science for Data Science for Sustainable Development, or DSSD. We're a tech nonprofit providing data science and GIS services to social good organizations in the conservation and development spheres. So this research on deforestation monitoring is supported by DSSD, along with our partners at the Institute for Integrative Conservation and the Global Research Institute at William & Mary. We wanted to say thank you for having us speak at this masterclass. So thank you to Geo Sakhi and Women in Geospatial Plus. And today we'll speak about our research aims with deforestation monitoring, progress we've made so far, and the next steps we'll be taking to create our end product. So when it comes to tracking deforestation, there's a range of remote sensing techniques that can be applied. And oftentimes accurate deforestation monitoring becomes a cocktail of these various techniques. So forest degradation monitoring approaches can usually be sorted into two categories. The first tracks canopy cover changes, as well as changes in proxies to deforestation, such as illegal logging. It highlights degraded versus intact forest cover and slow processes like regrowth. And the second category includes approaches that quantify forest loss and gain in above ground biomass using electric, optical, or EOS sensors, LiDAR that tracks canopy height and cover change, and radar. This also looks at changes in carbon stock, which are pretty small and difficult to detect, but they give a pretty specific reading of deforestation, more so than other remote sensing techniques. But we wanted to focus on the first category of these monitoring approaches and specifically narrow in on the breaks for additive season and trend, or BFAST method of automated change detection and time series of satellite data. So say you have 16-day composites of normalized difference vegetation index, or NDVI data, with varying amounts of seasonality and noise. This can be seen in the time series on the right. So when BFAST is applied, it can robustly detect abrupt changes within the time series and then characterize both the magnitude and temporality of those changes. So this early warning flagging system, made possible by BFAST, allows for near real-time deforestation detection. And the crux of our work this summer was to firstly understand the analytical potential of BFAST, but then to also understand how to best communicate BFAST insights to conservationists, researchers, and other stakeholders concerned with deforestation. Do you want to do the next slide? Yeah. So we translated our goal into about 3 different prongs. The first being the application of the BFAST algorithm across a wide geographic range with near real-time insights. So BFAST is most often applied using the R scripting language and automated MODIS NDVI data downloading. And this method requires a lot of memory and storage, and it's not necessarily the most reliable when inspecting BFAST on a large geographic scale. So the challenge of our project was finding the proper platform and maybe move away from the R scripting language to accommodate our computational needs, large satellite imagery downloading, and then application of this method. So our second goal involves simplifying access to BFAST for the non-technical user. As I just talked about, it's usually used with the R scripting language, but not necessarily everyone who wants to use this. for deforestation monitoring has that programming background. Also, BFAST has a lot of different input parameters that aren't necessarily inherent to a non-technical user or someone with a data science background. So how could we design an app with easy input parameters and an output that conveys a simple message of where did deforestation likely occur? And then our last goal is how can our findings contribute to wider discussions on deforestation monitoring capabilities? So do you want to do the next slide? Yep. So Google Earth Engine proved to be the platform best accommodating to our computational needs. And for those unfamiliar, Google Earth Engine is a planetary scale cloud-based platform that has a multi-petabyte catalog of different geospatial and data sets and satellite imagery. It's what you use if you want to bulk download Landsat imagery or MODIS or Sentinel, and it also has a lot of other geophysical and demographic data sets, ones that look at climate variables and atmospheric data. So about 1 year ago, the BFAST monitor, which typically is called using the R scripting language, was re-implemented in Google Earth Engine with JavaScript. And we were given permission to use this pixel-based variation of BFAST for our project, and as I said, use the JavaScript-based platform for it. So this variation of BFAST in Google Earth Engine models expected behavior of time series and identifies the pixels that deviate significantly as breakpoints. And it also harnesses the normalized difference moisture index and derives data from Landsat 5, 7, and 8 imagery. So now I'll pass it over to Maeve to talk more about the analysis and work on Google Earth Engine.
So the code written by the researchers in the implementation of BFAST monitoring paper left off with a layer of pixels shaded by their predicted magnitude of deforestation. The leftmost picture is a screenshot of this output. The larger square layer in red is the output of their BFAST code calculated from a Landsat tile, with the pixels representing the magnitude of deforestation detected. The blue rectangle inside that is the region of interest which we are focusing on. We decided that a simpler version of this layer with polygons to show regions of deforestation would be the best way to visualize the information for conservationists and non-technical people. From there, we decided on a threshold of magnitude with which to consider a pixel as deforested. With this, we then reclassed the raster into a binary, with zeros meaning no deforestation detected and ones meaning deforestation was detected. This layer can be seen in the middle photo, with the black pixels representing the deforested area. Next, we created a grid across the region of interest. This grid is a feature collection made up of rectangles, each with 1 kilometer squared area. Using this grid, we then clipped the binary raster of detected deforestation to each of the rectangles, taking the average value per rectangle. Using this final layer, we chose to display only the rectangles with a certain average value of deforestation coverage. This can be seen in the rightmost photo with the detected regions in red. So each red rectangle represents a 1 kilometer squared area where significant deforestation was detected. So now on to our demo of what we have right now for the web app. So this is the idea we have for what our application will look like. It's very base right now, and we plan to add a lot more. The idea for this is this application is for the user to choose an area of interest for monitoring, either by clicking on the map to highlight a region or inputting coordinates. Once the user chooses an area of interest, they will then specify the year they would like to start their monitoring and what year they would like to end their monitoring. Once they have chosen their parameters, the app will calculate the BFAST magnitude and find the regions with the most deforestation, displaying a layer like the one showing now. As you can see on the right, we have a very baseline prototype for what the legend might look like on the web application. In the future, we plan to add a lot more options for customization. For example, a more efficient way to choose the years, options to look at the point or polygon data, and ways to export different formats of data. Right. Now back to Laura.
So what are some of our next steps? Maeve talked about a couple, but I'll speak about some of the more methodology related next steps, and then Maeve will continue and finish at the end with steps related to building the app. So we're currently deciding a process for determining a threshold at which we can define a pixel as a part of deforestation. And as explained before, the magnitude is computed for each pixel associated with a breakpoint. Magnitudes are also computed for ones not associated with a breakpoint, but we would isolate the ones that have a timestamp associated with them. And then considering only the presence or absence of breakpoints to define deforestation is not sufficient. So as breakpoints are usually associated with either positive, negative, or zero magnitudes, and those don't translate directly to deforestation. So to avoid false positive deforestation detections, only breakpoints with a magnitude above a certain threshold should be considered, but the challenge is deciding what that threshold is going to be. And that's going to be dependent of a study area. And then it's also going to need to be calibrated and calibrating the magnitude threshold against reference data. So we're exploring the process of deciding a threshold through visual interpretations of NDMI magnitudes, and this encapsulates choosing 50 to 100 random points associated with a break in a study area. And then we would cross-verify if deforestation actually occurred at those areas with either Google Earth images or planet.com imagery, something really granular where you can visually affirm if deforestation really happened or not. So for the pixels we can visually confirm as being attributed to deforestation, we would look at the ranges of magnitudes and then choose a threshold based on the minimum value of that range. And this manual process is definitely not one that can be easily automated and integrated into the web app right now, but definitely something that we want to think about for the future, especially to customize this per study area and per year. And then next slide. So then we also need to think about what spectral index is most suitable for detecting clear-cut deforestation. This also depends on the study area and then also, the year that we're looking at for deforestation. And in our web app, we use NDMI right now, mostly because it's the one built into the original code that we're adding to and building our web app off. So as a reminder, the normalized difference moisture index, or NDMI, represents the ratio between two infrared red bands. So that's NRI and shortwave infrared. And then NDVI, which is probably one of the most well-known vegetation spectral indices, is it's really successful because it allows comparisons between interannual and seasonal changes in vegetation, and it represents a ratio between the near infrared and red bands. For Landsat 8, this would be bands 5 and 4 respectively. So when analyzing deforestation in a region of interest, it really makes sense to cross-validate results when applying the different indices. So out of, say, 100 random pixels in a study area, how many were correctly identified as deforestation when NDMI was concerned versus when NDVI was concerned? So a suitable spectral index combined with a proper threshold is really key to accurately determining deforestation throughout an entire area of interest. And as we talked about before, these are definitely considerations for the future, and building out this app so deforestation is customizable, deforestation detection is customizable per region of interest. And I'll just pass it over to Maeve, who will finish up with more about the app.
So for the next steps of our research concerning the app, we would like to pick a case study to verify the results of our application, like Laura said, and then we will continue to fine tune and simplify our coding and work on the presentation of the web app. We hope to create a fully functional and interactive application, providing the information necessary for conservationists while also being easy to understand for non-technical people. When the web application is finished, we will create a website to host the app and give further background information on what BFAST is, how to use the application, and how to interpret the results, and maybe adding some how-to videos to further help people figure out how to use this application. We hope that this will be a resource for people, no matter their technical or GIS skills, to give a correct and easy to understand formats of data on the health of forests.
And for any questions or inquiries about our app, you can reach out to us. Our emails are listed. Also, once this code will be public, as well as the web app, that will be public at the end of August on our GitHub at Data Science for Sustainable Development. As Maeve said, I hope this was helpful, and this can be used in the future for deforestation monitoring. So thank you again to Women in Geospatial and Geo Sakhi for having us a part of their masterclass.
Now this is the second video about CODED in Nepal.
Hello, my name is Crystal Wespestad. In this talk, I'll be highlighting the usefulness of remote sensing technologies in environmental mapping context, and most especially for the purposes of forest monitoring. I work for Spatial Informatics Group, which is an applied science contracting company that specializes in spatial analytics of ecological, social, and economic sciences to understand the effects of management and better inform environmentally focused decision-making. We recently worked with the Forest Research and Training Center of Nepal's Ministry of Forests and the Environment, along with several team members from other groups to map forests in Nepal. In this talk, I'll give you the highlights of that paper entitled Remote Sensing Time Series Analysis of Forest Disturbance Detection in Nepal, and use it to show you one example of how remote sensing technologies can be used in an applied context. Preserving forests is important because they fight climate change by sequestering carbon, converting greenhouse gases to breathable air, and additionally, they are an important habitat for many species. As many countries progress towards assessing and implementing results-based payments under the REDD+ program, where countries are given monetary incentives for keeping their forests rather than converting them to other land uses, forest-related emissions from both deforestation and degradation must be assessed within a reasonable degree of certainty. Nepal is one of the countries participating in this effort. Mapping and estimating the area of forest degradation deforestation, which is also called activity data for reporting purposes, is the main forest monitoring objective that can be achieved through remote sensing techniques. Let's first define some terms. Both deforestation and degradation can be referred to as forest disturbances. Deforestation is a well-known concept where forested land is permanently and totally converted to non-forested land cover. This can occur naturally or be human-caused. There is no universally accepted definition for degradation. The United Nations Food and Agriculture Organization, FAO, defines degradation as the reduction of the capacity of forests to provide goods and services, while the Global Forest Observation Initiative, GFOI, has described it as the disturbance caused by human intervention in a forested landscape that results in carbon emissions, but not a land cover change. For our project, we will be referring to degradation as the temporary reduction and subsequent recovery of NDFI and vegetation cover without a land cover change from forest. NDFI is the Normalized Difference Fraction Index, or is sometimes referred to as the Normalized Degradation Fraction Index. I'll explain more about this index in a minute. We use this definition because that is how degradation is defined with the tool we use to detect it. It essentially means that the forest canopy was partially or totally damaged for a period of time, but not so badly that it was permanently converted to non-forested land cover. I also want to talk a bit about remote sensing. For a bit of background for those who are not using these techniques on a day-to-day basis. Remote sensing is defined as observing from a distance the physical characteristics of an area or surface by measuring reflected and emitted radiation. The visible light spectrum we see every day is just a small piece of the electromagnetic spectrum. Humans do not have the capacity to see all types of light or radiation. Each type of radiation has a different frequency. Those types of radiation with high energy, like blue light or X-rays, are made with more compact waves than those with lower energies. Red light, infrared radiation, and radio waves have much longer wavelengths and are lower energy. These properties make each type of radiation interact with the surface in different ways. Sometimes the radiation bounces off the surface, while sometimes the radiation might be absorbed with that same material. The easiest example is that of a leaf, which appears green because that material reflects green light, but absorbs the other colors of light that we can see. Going deeper, we can tell more about the plant that leaf is on by what proportions of each type of radiation it reflects and absorbs. It turns out that healthy plants reflect a lot more near-infrared radiation than unhealthy plants do. You might be familiar with the vegetation metric called NDFI, or the Normalized Difference Vegetation Index. Remote sensing scientists use the levels of reflected radiation in the near-infrared spectrum and the red spectrum to make this calculation, and it serves as an indicator of plant health. We are taking a step further than that and calculating a metric called NDFI, or the Normalized Difference Fraction Index, which is used to monitor disturbances in the forest canopy. How this is done is described in Souza's et al. 2005 paper. The spectral patterns reflected by several different land covers are observed, and an average reflectance signature is calculated. We use the patterns defined by Souza et al. For green vegetation, GV, non-photosynthetic vegetation, NPV, shade, and soil. This is called linear spectral mixture analysis, or SMA. When there are greater portions of soil and non-photosynthetic vegetation, the NDFI value is low and indicative of a degraded forest conditions or naturally sparse canopy cover. This is a map of NDFI that shows what these looks like in an area with selective logging. You can see how logged areas and roads both stand out in the bright yellow color. The tool we chose to use for the analysis of forest disturbances in Nepal is called CODED, or the Continuous Degradation Detection Algorithm. It was developed by Eric Bullock, who is one of the authors on our paper. CODED is a free and open source tool that runs on Google Earth Engine. By default, CODED uses freely available optical Earth observation imagery provided by Landsat satellites, which are already available on Google Earth Engine's data catalog. The combination of a free and open source algorithm, freely available imagery, and comprehensive documentation make CODED an attractive tool for groups with limited budgets and capacity for developing custom-built solutions for detecting forest disturbance. Now let's go over the methodology within the CODED tool. CODED can be run as a GUI, so you do not need to know all of these details to use the tool, but I think it's helpful to know, especially when you want to adjust the parameters to better fit the region you are analyzing. All Landsat imagery is automatically pre-processed to mask out clouds. Then CODED uses sub-pixel spectrum mixture analysis, SMA, using defined spectral signatures of different land covers, which I described earlier, and uses this to calculate NDFI. This is repeatedly performed for every pixel over time, so NDFI can be evaluated as a time series. This process can detect sub-pixel scale changes of the spectral signature reflected by the land cover. A baseline NDFI pattern, which accounts for seasonal changes, is established first. From that, the future NDFI values can be predicted. If the observed NDFI is nearly different from the predicted values, and this occurs several times in a row, then the algorithm flags this as a forest disturbance event. It is categorized as either forest loss or forest degradation, depending on whether the land cover type changed from forest. Training data points of forest and non-forest land cover are required by CODED in order for it to determine whether this land cover change occurred during the disturbance event. So how did CODED do when we applied it to our study area in Nepal, the Terai region? The Terai is an ecologically complex place that has been experiencing more urbanization and population densification due to migration from other physiographic regions, which has led to a higher demand for forest products and left the forest vulnerable to several different drivers of deforestation and forest degradation. We began the process by gathering 3,631 training data points to train CODED on what counts as forest and what does not. Then we began testing various parameters and having those on our team with local knowledge of the forest disturbances in the area perform visual evaluations of the results. Some tests clearly over or underestimated deforestation degradation. It became clear that we needed a more thorough understanding of the impact of each parameter on the results. Therefore, we decided to pursue a more systematic visualization of the results on a sample site before spending time on writing the code on a full study region. These are some example results of the impact of systematic testing of the four most impactful parameters, which are the forest mask, the number of consecutive observations required to define a disturbance event, the chi-squared value, which controls the size of the window for detecting statistical change, and the magnitude threshold, which is a post-processing parameter that filters out low magnitude changes that may be false positives or not considered severe enough to count in official mapping. In this example, there were a few regions that we knew from on-the-ground observations had been degraded. These are the rectangles that you see in the 2020 infrared image and in the example disturbance maps. The most obvious example here shows how setting a magnitude threshold that is too low can lead to severe overestimation of degradation, whereas a threshold that is too high could ignore many of the degradation events that are often by definition low severity changes. Based on our experience in Nepal, we recommend that future users of CODED for forest disturbance mapping thoroughly test one parameter at a time so that the users can clearly observe the impacts of adjusting that parameter within their particular environment. Different forest types require different thresholds due to variance in canopy type and the expression of deforestation and degradation events on that forest canopy. You can only really know how well your parameters have been represented of the true conditions through a complete accuracy assessment with high resolution reference data. We used Collect Earth Online to do this. Collect Earth Online, or CEO, is a custom-built open source satellite image viewing and interpretation system developed by Surveyor, a joint NASA and USA program, and with the collaboration of several regional technical organizations, including the company I work for, Spatial Informatics Group. CEO promotes consistency in locating, interpreting, and labeling reference data for land cover change validation. It offers a collaborative and online environment for collecting reference data points. You can think of reference points as the true answer to whether a location has been degraded or deforested within the study period. These points are collected by team members looking at high resolution imagery and graphs, in our case, of NDFI over time. Once these points are collected, we can compare them to those same points that were mapped by the CODED algorithm. The hope is that the map agrees well with the true conditions as labeled by the interpreters. This is an example of what an interpreter we're looking at when deciding whether a disturbance event occurred at that point location. In this case, the location is clearly forested and has a high NDFI in the left image, but sometime later, as in the right image, the NDFI drops and it looks like a river has migrated into that location. This is an example of degradation due to flooding. Here's another great example of degradation due to river flooding or river movement. This is degradation and not deforestation, because you can see in the graph and the last image that the forest has recovered and the land cover type was not permanently changed. This last example is of a degradation event likely caused by a conversion of forested land to farmland. You can see the seasonal variation in NDFI values from the growing and harvesting of the crop as it slowly becomes reforested. So after the interpretations in CEO, where we analyzed the comparison of the accuracy of the very different iterations you ran with very different parameter combinations, it took us 11 tries with several tests on small sample regions in order to finally settle on a final map with an overall map accuracy of 91.7%. This chart highlights how important carefully testing your parameters is for achieving reliable results. Our final map indicated that in the Terai region of Nepal between 2010 and 2020, nearly 3,000 hectares were deforested. But that seems very small compared to the 105,650 hectares of forest that were degraded. Clearly, forest degradation cannot be overlooked as a major player in forest mapping for estimation of greenhouse gas emissions and carbon storage loss. So the key points I hope you take from this talk are that degradation is important to quantify, not just deforestation. That thoroughly tested parameters of the mapping algorithm, whatever it may be, are important for finding the appropriate systems and settings for your region and for assessing the accuracy of your area. Testing out different parameters improves your accuracy. And overall, I hope you saw one important example of how remote sensing tools are being applied to real-world problems like climate change. These are the sources for this talk. We'd love for you to check out our paper, which is at the top of this list. And if you are interested in trying this process yourself, the coded scripts are freely available at this link. Thank you so much for listening.